Hi everyone, it's Mr. H here, and today's lesson is on specific heat capacity. If you have gone and seen the Eureka video, specifically the heat as energy video, you know that it takes 4,200 joules of thermal energy to increase the temperature of 1 kilogram of water by 1 degree Celsius. Just for the sake of some fun and just because Eureka videos are so great, let's watch 1 minute of that video now.
What is the unit of measurement of heat? Well, what is the unit of measurement of energy? The joule, of course. So logically enough, since heat is energy, the unit of measurement of heat is also the joule. We know that 1 joule is the amount of energy needed to exert a force of 1 Newton through a distance of 1 meter. This means that if Count Rumford wants to raise this kettle of water, which has a mass of 1 kilogram, or a weight of 10 newtons, through 1 meter, he'll have to expend 10 Newton meters of energy, or 10 joules of energy. But when we're dealing with heat as energy, instead of raising something through a distance, we raise its temperature through a certain number of degrees Celsius. In fact, scientists have worked out that it takes 4,200 joules of heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. Let's see Count Rumford do just this with his kettle of water, which is now at 15 degrees. The Count is now moving the water with his 8-beater. He's expending energy, and he's producing heat. Just enough heat to raise the temperature of the kilogram of water from 15 to 16 degrees, 1 degree Celsius. And it cost him exactly 4,200 joules of energy, or heat, to do it.
Now, I hope you realize how significant this 4,200 joules is, because to raise 1 kilogram of water a distance of 1 meter was approximately 10 joules of energy. So we're talking about 420 times as much energy to raise that 1 kilogram of water by only 1 degree Celsius. Fantastic amount of energy. It's a lot of energy. And so more specifically, it's 4.18 times 10 to the 3 joules. It's not really 4,200. They've rounded it in the video. And the other thing worth noting is that when they referred to as heat as the video, we're calling thermal energy. Heat is the transfer of thermal energy. It is the action of the thermal energy, is the verb, if you will. So we can make this a measure of specific heat capacity. Well, what is that? Well, it's the amount of energy in joules needed to increase a temperature of 1 kilogram of a substance by 1 degree Celsius. The amount of energy in joules needed to increase the temp of 1 kilogram of water not just of water, but any substance, because we have specific heat capacities of different substances, by 1 degree Celsius. What are the units of specific heat capacity? Well, it's the joules for 1 kilogram per degree Celsius, so that's our units, joules divided by kilogram degree Celsius. And there you see for water, it has a fairly high specific heat capacity compared to many other materials. So for 10 kilograms of water, with C being 4.18 times 10 to the 3 joules, that means we would have to use 10 times the amount of thermal energy to warm that up, because we'd have 10 instead of 1 kilogram. There's another thing we wanted to find today, and that is the quantity of heat. The quantity of heat is the amount of thermal energy transferred from one object to another. The amount of thermal energy transferred from one object to another. And so if you're going from a hotter object to a colder object, that amount, that Q, is positive. If you're going from a cold object to a hotter object, that Q is actually going to be a negative because you're losing that thermal energy. So the equation that we use to calculate that is Q equals mc delta T, where Q is, as we just defined, the quantity of heat in joules. M is the mass in kilograms. C is the specific heat capacity. That's going to be measured in capacity. That's going to be measured in joules per kilogram degree Celsius. And delta T is the difference in the temperature. So it's the second temperature minus the first one, or the final minus the initial temperature. And so these are the temperatures. Capital T for temperature. And so if a substance absorbs energy, then that change in temperature is going to be positive. If it releases energy, it's going to be negative, and that's what's going to make these Q values either positive or negative. To transfer milliliters to mass, we use the density of a substance, and usually we have the density given in grams per milliliter. For water, this is really simple to do. So if you're given a volume in milliliters, to change it to grams, it's actually 100 grams is equal to 100 milliliters. So you just change the units. You don't have to do anything else. For other substances, you would be given the density and you would have to translate the units, just like we do with normal unit analysis. All right, so let's look at an example of how this works. If a pot of 500 milliliters of water is warmed up from 21 to 100 degrees Celsius for T, how much thermal energy does the water absorb? Well, the mass is 500 milliliters, and I already stated the fact that it's going to be 1 gram is 1 milliliter, 100 grams is 100 milliliters. But just so that we see this for other things that might not be water, let me just show you how this works. We would say I want to change units to grams, and then I want to put it in kilograms. So we know there's 1,000 grams in 1 kilogram, and that's going to get my units of kilograms. And so that's going to give me 500 divided by 1,000, or 0.500, I guess it's 500.0, so 5.000 kilograms. That's the mass. The change in temperature, you'll notice that its initial temperature is 21 degrees Celsius, and its final temperature is 100 degrees Celsius. So we're going to take the final temperature, 100.0 degrees Celsius, and we're just taking the 0.0 just so we're clear on how many sig digs we have. And we're going to subtract the 21.0 degrees Celsius, which gives me a temperature change of 79.0 degrees Celsius. It's a positive difference, meaning that the Q is going to be positive. It's the thermal energy we've gained. The specific heat capacity of water is 4.18 times 10 to the 3 joules per kilogram degree Celsius. And we can go ahead and we can solve for Q. That's what we're after. We're trying to find the amount of thermal energy that is Q. Q is equal to MC delta T, and it's a matter of just subbing these values in and solving that. 0.5000 kilograms. The C is 4.18 times 10 to the 3 joules per kilogram degrees Celsius. And the temperature is 79.0 degrees Celsius. Now, pay attention to the units here. The degrees Celsius cancels out. The kilograms cancels out, and we're left with units of joules. And so the value we get here is 1.65 times 10 to the 5 joules. And we would conclude, therefore, the water absorbs that much energy. The water absorbs 1.65 times 10 to the 5 joules of energy. If that was a negative value, if it went from 100 degrees Celsius back to 21 degrees Celsius, as that T sat in room temperature, we would say that the water released that amount of energy. So it absorbs because it's positive. If it was negative, it would be released. You might want to just note that at the side. All right, so a couple of things to wrap this up and to do one more example together. The first thing is this. If something loses thermal energy, Q is negative. I just mentioned that. you can rearrange for any of these variables, and we can even break this apart. We can take the delta T and break it apart for T2 minus T1, and if I knew everything else, I could solve for one of those temperatures. I could solve for the mass. I could solve for the specific heat capacity. The principle of thermal energy exchange, just like the conservation of energy, says that we can't lose energy. We can't gain it. We can only transform it between forms. So when thermal energy is transferred from a warmer object to a colder object, the amount of thermal energy released by the warmer object is the amount that is gained by the colder object. So Q release, this is a negative value, is going to be absorbed by the other object, that's the positive value, and together they're going to equal 0. So here's the example that we're going to finish up this video with. Scientists are trying to find the specific heat capacity for a new molecular compound of metal. They place this metal of 0.5 kilograms at a temperature of 90.0 degrees Celsius, and I'm just going to add a 0 here. Let's say it's got 2 sig digs, because everything else has 2 or 3 sig digs. Temperature of 90 degrees Celsius. They put it in 0.40 kilograms of water. That water initially was at 10 degrees Celsius. So what's going to happen to the water, just intuitively, you've got a hot piece of metal in the water. It's going to warm up the water, and it's going to eventually come to an equilibrium temperature, meaning the water and the metal reach the same temperature. And that temperature is 17.3 degrees Celsius. It says determine the specific heat capacity of this new metal, and we're going to do this below. So I'm going to separate this out with our givens, and I'm going to write my absorbed values and my released values. It just helps us to organize our thoughts by doing this. And so the absorbed amounts are the water, because the water is going from 10 to 17.3 degrees Celsius. And the material that's releasing the energy is the metal, because it's going from a very hot temperature to a colder temperature. So that's going to be the negative value. This is going to be the positive value. So the change in temperature of the water is the second temperature of the water minus the first temperature of the water. The first temperature of the water. And so we can see here that it started at a temperature of 10 degrees Celsius and ended up at 17.3 degrees Celsius. So take that minus 10.0 degrees Celsius. You can put it in brackets if you want. You don't have to here. And yet with 7.3 degrees Celsius is the change in temperature of the water. Likewise, you can see that the change in temperature of the metal, in this case, is changing in temperature from 90 degrees Celsius to 17.3 degrees Celsius. So it's, again, the second temperature of the metal minus the first temperature of the metal. So 90 degrees Celsius, 17.3 degrees Celsius is where it ends, and then it started at a temperature of 90.0 degrees Celsius. So in this particular case, it's releasing it's cooling down by 72.7 degrees Celsius. Now for water, we know the specific heat capacity of the water. We know it's 4.18 times 10 to the 3 joules. And I should note here that page 281 has the specific heat capacities. So you should use that if you don't know the specific heat capacity, but you know what material it is. You can go ahead and see that on page 281. It's a chart there on the side that shows that to you. We also know that the mass of the water is 0.40 kilograms. The mass of the metal, we're told, is 0.50 kilograms. Let's see if I can get my M to show up properly. There we go. 0.50 kilograms. And my specific heat capacity of the metal, that is what I want to solve. So with that in mind, let's go ahead and start with this idea of the released and absorbed energy. So we know that Q absorbed plus the Q released is equal to 0. And this is our required value. This is our analysis now that we're working on. Rearranging this equation tells me that the Q absorbed, oftentimes you'll rearrange this equation, is negative Q released. So if you wanted to start with that, I suppose you could start with that too. But we now need to break it down. And so we know that the specific, or that the Q value, the thermal energy, is the mass times the specific heat capacity times the change in temperature. And that's the water on the left because that's absorbed. And then on the right, we have the metal. And so it's the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal. The value that we're trying to solve is this. So we're going to divide both sides by negative mass of the metal times the change in temperature of the metal. Be careful with your subscripts here because we can't cancel out delta T and we can't cancel out the mass because remember those are different masses for different objects and different temperatures that have been changed for the different objects. So the specific heat capacity of the metal is equal to this divided by anything else. So this is going to cancel out, this is going to cancel out, and I'm going to sub those values in. So the mass of the water, 0.40 kilograms. The specific heat capacity of the water was 4.18 times 10 to the 3 joules per kilogram degree Celsius. I didn't write the units right there, kilogram degree Celsius up above. And then the change in temperature of the water was 7.3 degrees Celsius. We're dividing all of that by negative. We're dividing by negative. The mass of the metal was 0.50 kilograms. And you'll note that it's negative because I divided that side by negative. I should have done that side by negative as well. So negative 0.50 kilograms times the change in temperature of the metal, which was negative 72.7 degrees Celsius. There's my two negatives making this a positive. Positive divided by a positive gives me a specific heat capacity that's positive of 336 joules per kilogram degrees Celsius. So my solution is here, and then my statement. I'm going to end with the statement. Therefore, the specific heat capacity of the metal is to 2 sig digs would be 3.4 times 10 to the 2 joules, or 340 joules. Now, if you look at page 281, you can actually see that that's fairly close to copper. Copper is 3.8 times 10 to the 2 joules. So it's somewhere a little bit lower in specific heat capacity than copper. The last thing worth noting as you look at page 281 in that chart is you'll notice that metals have a much lower specific heat capacity than things like water. And that's because water is considered an insulator. Things that are insulators have a very high specific heat capacity, hence it's very hard to change the temperature. Things that are conductors or metals have a very low specific heat capacity. Therefore, it's very easy to change the temperature. So again, as always, if you have questions, feel free to reach out, ask for help, and I'm happy to help. Hope that makes sense, and all the best.